Hmm. Hmm. Okay, so we did this question, and the next question is super easy. You can do it yourself because it's the same graph, same thing, and everything is the same. The next question is also very easy. You can do it yourself. Same homework and homework. Okay, this is also homework. This is the same question from the previous one. Now, today we would like to discuss the concept of distance of closest approach, basically. And I just want to tell you that. Hold on a second. That's not fair. Wait a second. Okay. So now let's look at this way. So what happens is that if you notice that this charge is positive and this charge is also positive, which basically means as you approach this, there is a great force of repulsion, right? Because the force of repulsion from the other charge will be on this charge like this. Now what you need to do is this charge needs to do work against this repulsive force, right? Now, if you need to do work against this repulsive force, it basically means that you gotta have the charge must have some kinetic energy initially that would convert to the potential energy, and that's where you're doing work against the force, so obviously your potential energy is increasing. So we got to learn that. All right, is it clear, everyone? So then we should realize that because we have come to this conclusion that kinetic energy is going into potential energy, and kinetic energy is given by half mv square, and potential energy is given by change in electric potential times charge, like that. So sometimes the examiner is going to give you like to find speed, and you can multiply like change in potential times charge, and then you can divide it by m, and then you can take the root like this, right? So this speed that you see right now is the speed of the closest approach, because the greater the speed is going to be, the greater the distance it would cover to reach closer to that particular positive charge as well. All right. Now, alternatively, you can also change this, like you can write it as 2. And since this potential is given by, 2 times kq over R over M, like that. So you can, put the potential value here. So obviously, then the equation would be 2kqq over m times r and under root. That will also give you the same thing. All right, so you can change that. That's not a big deal. If you have any questions here, please let me know. Now these both derivations are important because in the sense that the examiner will ask you for these and you should better know how to deal with them. Otherwise it's quite simple. There's nothing fancy about it at all. Now
it can't go beyond this distance T.
Sorry?
It can't go beyond the distance T.
No, that's what I was about to tell you. You can add a note that basically when two positive charges they basically touch each other, that's when fusion occurs. All right. Now, to successfully fuse two charges, you need to give appropriate amount of kinetic energy. So that is the reason that when we say fusion requires a lot of heat and pressure. So the reason why we're saying that it requires high temperatures and high pressure, because at high temperatures it basically comes closer, and at basically high temperature the kinetic energy is very high. That helps in getting them close to each other. Do you understand? Okay. All right. Should I go forward then? Okay. So for this question, which is basically the first type of question that they're going to ask you, in this question it says that define electric potential. So you guys already know this now, so that would be your homework. But then it says that a charged particle is accelerated through rest, and it says where q is m the ratio of the charge mass of this. So you just need to show this expression. We have already shown it, like in the previous example, like what I did it, so you can try this on your own. But we're going to start from here. So in this one, they have said the specific charge, and if you look at the units here, you might realize that this unit is basically charge per unit mass, because there's coulomb per kg and moving vacuum through a fixed metal sphere, right? So they say that initial speed is this when it is long distance from sphere. The sphere is positively charged and a potential of plus 4, like basically the potential at its surface is this much, right? So it says use your expression to determine the whether will reach the surface, whether they will fuse or not, right? This is what we are looking at. So in order to touch the surface, we need to find the required velocity. All right, so we're not going to use this velocity because that's the initial one. We can compare it later on, and because the expression was already given, we know the expression is v over 2 vq over m, like that. So now, sorry, I had to write V here. Okay. So 2 times the potential that we are trying to reach is 470, and the charge on the other sphere is charge over mass is given, which is this value. We're going to write 9.58 times 10 raised to 7 and root of it. What you get then?
3.0 times 10 raised to power 5.
3.0 times 10 raised to 5 meters per second. Now this is the velocity that is required, right, to make this happen. But our velocity is less than this. So we're going to say that initial velocity, which is 2.5 times 10 raised to 5, is less than the required velocity, which is 3.0 times 10 raised to 5. So hence they do not touch. All right, is it clear, everyone? Do you guys understand this? Any questions, please let me know. Okay, pretty good. So speaking of this then, we are gonna basically go to the next part, and this is sort of a other type of question, where now instead of giving charge to mass ratio, they've just given you the value of the charge itself, which is 79 and they say that a large distance from gold nucleus, the alpha particle has a kinetic energy which is 7.7 times, like it's just energy, and it says the alpha particle does not collide with gold nucleus. Show that the radius of gold nucleus must, wait, what? Okay, so it says if they do not touch, so we need to show that the radius of gold nucleus must be less than this. So we're gonna just check this again. This is a checking question. So now we have kinetic energy. We should write that kinetic energy is given by basically the potential. It's gonna go towards the potential energy. Okay, like that. So this whole kinetic energy is going to convert to potential, and we need to find, I think, the radius in this. So we're going to write 7.7 times 10 raised to minus 13. Now, to find the potential, because change in potential times charge, and we don't have the potential, but we know it is kq over r times q. So we're going to find this. K will be 8.99 times 10 raised to 9. The charge on gold nucleus is 79 which basically makes it 79 times 1.6 times 10 raised to minus 19 coulombs, because that's the value of E, times the small charge is alpha particle. Alpha particle is 4.2. You should remember that. So it's 2 times 1.6 times 10 raised to minus 19. And then we are going to find this radius. That how much does it reach? So can you help me find the radius, please?
So 4.7 times 10 raised to minus 14.
4.7 times 10 raised to minus 14.
Yeah.
Now this is the value that we reach. It means that if it has like reached somewhere at a certain value, which is like 4.7 times 10 raised to minus 14, and because it says they do not collide that means that obviously the only way they would not collide is that the gold nucleus radius must be smaller than this. You guys agree? So if they do not collide, the radius of gold nucleus must be less than 4.7 times 10 raised to minus 14, as that is the value it has reached. If it had, reached a very like a value which was like smaller than this, then we would say okay, it might have done that. So that's fine. Then in the next one it says determine the acceleration of alpha particle for the separation of this between the centers of gold nucleus and alpha particle. Now we got the separation, and we know that F, the force, is kq over r squared. So we're going to find the force first, and we are looking at the acceleration of alpha particle. So again, 8.99 times 10 raised to 9 times 79 times 1.6 times 10 raised to minus 19 times 2, 1.6 times 10 raised to minus 19 divided by 4.7 times 10 raised to minus 14 whole square. What you get for the force, please? Yes, please. What you get?
$16.5.
Are you sure? 16.5 newtons. Gothica. Okay, I don't know. Could be this. I have no idea. But this seems a very weird answer. Okay, sorry. I was supposed to open the calculator. Let me just try and do this. So 8.99 times 10 raised to power 9 times 79 times 1.6 times 10 raised to power minus 19 times 2 times 1.6 times 10 raised to power minus 19. Okay. And what you get? 4.7 times 10 raised to power negative 14 and then whole square. Oh, you're right, Gautika. All right. And then we're going to use F equals to ma to do that. The interesting thing is that the mass of alpha particle is 4 too. So we got to write 4 times, the value is u actually. So u is taken as 1.66 times 10 raised to minus 27. Now can you find the acceleration, please? Okay, go on. Other lazy people, you should also do it. That's not fair with Gautika, you know.
Says 2.5 times 10 raised to 27.
10 raised to 27. Okay, meters per second. So this seems like a likely answer, which is probably correct. Now, keeping that in mind, then it says in an alpha scattering experiment, the beam of alpha particles is incident on a very thin gold foil. Suggests why the gold foil must be very thin. The gold foil must be thin because if there are multiple, there are multiple layers of nuclei of gold foil, so when alpha particle would come, it would get attracted by different sides. All right, is it clear? So the main reason at that time to do so was to make sure that alpha went under single interaction. It would not have to go through multiple interactions, and that would make studies a bit different. So that's why we had to make sure that it was so thin that they would align in just one line. Is it clear, everyone? Any questions? Mokshit and Suman and Aman and Rafi, Ahmed.
Yes, sir.
And the other Ahmed is not here. Munib, Fahar.
Yes, sir.
Okay, cool. So now these are some practice questions that I wanna basically you guys will do. So all these practice questions I put it intentionally because the reason is that this chapter has a confirmed question every single time, so you can't just miss it, and you gotta practice it, and it's just free 10 marks in any case. So I put a lot of them this time because I just want you to how did this come up? I don't know. This is not fair. This question came up. Chalo, never mind. You can practice this too. All right. So I believe we have done the whole. Yeah, we finished this, and well, we finished it before time. That's not fair. And every time we finish something before time, I think it's best to now cover some paper 5 questions. Okay, so let's do that.
So can you please explain the A part again, the Golgi nucleus one?
Yes, why not? Where was it though? So gold nucleus part. Yeah. Gatika, where is it? It was this here. Okay. So in reality, if you remember that experiment from AS, you might remember that basically.
So not this one, the first part, the radius one.
This one.
Yeah.
Okay. So we are saying from center to center, the distance was 4.7 times 10. This is the closest it could reach, right? Right, Gatika? Now we are saying at this point, they did not touch. They did not collide. What does that mean? If they had collided, so that would mean that they would have touched, and then this distance is the distance that is equal to the radius, right? The only way they can touch is when they touch like this. Do you understand? Like that.
Yes, sir.
So because they did not touch, it means there's still space left even though it has traveled this much distance. Do you get it?
Okay. Yep.
All right. So I'm gonna